Okay, one more thing about FM and the noise performance of FM systems. We worked through in the last presentation the power spectral density of the noise at the output of an FM demodulator, and we determined that it has this kind of equation. N naught is the intensity of the background noise. Omega is frequency in radians. So N naught omega squared divided by AC squared, which is the amplitude of the carrier. And this power spectral density has a parabolic shape as illustrated here. So this equation, N naught omega squared divided by AC squared, will take this parabolic shape. And the thing with the parabolic shape is that it is zero at 0 hertz, and then it increases as the frequency increases. So there is less noise power down at lower frequencies. At small frequencies, there is less noise power than there is at the higher frequencies, which means that for our message signal, which would be an audio signal typically for an FM system, there's less noise interference for the lower frequencies than there are for the higher frequencies. So the FM broadcasters have cleverly taken advantage of this by filtering and equalizing the message signal in such a way that they put more power into the higher frequencies and they put less power into the lower frequencies, and they increase the signal to noise performance of FM even more than it is just simply by being FM. So commercial FM transmitters and receivers follow this kind of system. They start with a message signal X of t, and then they pass that through a pre-emphasis filter, which is a filter with a transfer function that will boost the power in the higher frequencies of the message signal, and so that it will compete better against the noise, which will inevitably be added. Then this signal is then transmitted through the FM transmitter. Additive noise is added in the channel, and then at the receiver it is demodulated. And then they follow that with a de-emphasis filter, which is carefully designed to match the characteristics of the pre-emphasis filter, so that it will it will equalize the message signal back to its original state. This is the transfer function for the pre-emphasis filter as a function of omega. K is some amplitude constant in the numerator, 1 plus j omega times tau 1, which is a time constant. And then the denominator 1 plus j omega times tau 2, which is a different time constant. And from that we can get the corner frequencies omega 1 and omega 2. And now want to draw a Bode diagram for this transfer function. So we've got this term that breaks upward in the numerator, and a term that would break downward as well. So this is the Bode diagram of the transfer function for the pre-emphasis filter. It's a constant k, and then we have our first corner frequency at omega 1, where the curve breaks upward and slopes upward is at 20 dB per decade, I believe. And then it has another corner frequency at omega 2 that slopes downward, so then the curve flattens off. So this is the frequency omega here. We typically would put this in hertz, but it's here shown as omega. Our input signal, the lower frequencies are amplified with a certain constant, but the higher frequencies are emphasized. More energy goes into the higher frequencies, and now this so that puts more more power in the high frequencies, less power in the, compared to the low frequencies. And this now is applied to the modulator. And the de-emphasis filter is has a transfer function 1 over 1 plus j omega tau 1, and that would give us the corner frequency omega 1, where the curve breaks downward at 20 dB per decade. And so the result is when the corner frequencies counter each other when you have the de-emphasis filter following the pre-emphasis filter. So for no distortion in the signal, the product of the pre-emphasis filter transfer function times the de-emphasis filter transfer function is a constant k for frequencies less than the upper corner frequency. So the upper corner frequency would be something like 15 kilohertz. Well, there's a standard for it. We can figure out exactly what it is. But so overall, it doesn't distort the signal when you take the two filters together, but it does, for the purposes of transmission, it does put more energy into the higher frequencies of the message signal. Now, with the de-emphasis filter in place, I want to find the output noise power. So I've put a little prime here to indicate that the de-emphasis filter is in place, and the output total noise power is found by 1 over pi times the integral from 0 to w. N naught omega squared over AC squared is the noise power spectral density, and now we multiply that by the magnitude squared of the de-emphasis filter. So 1 over pi integral 0 to omega n naught omega squared over AC squared. The magnitude squared of the de-emphasis filter is 1 in the numerator, and then the real part squared plus the imaginary part squared in the denominator. So that's 1 squared plus omega times tau 1 squared, and we're integrating with respect to omega. Let's see, this brings out everything that's not a function of omega. Integral from 0 to w of omega squared divided by 1 plus omega squared tau 1 squared d omega. And if you look up the antiderivative of that function, we get omega over tau 1 squared minus 1 over tau 1 to the third power times the inverse tangent of tau 1 times omega, and we're integrating from 0 to w. So you plug in the upper and the lower limits of integration, and we get this expression after a little bit of algebra for the noise power out with the de-emphasis filter in place. And that doesn't mean much to us until we compare that to the output power without the de-emphasis filter. This is without the de-emphasis filter. This is the result we got from the last presentation. So I can compare this output noise to the output noise with the de-emphasis filter. This gives us a noise improvement factor. This is gamma. So the output noise power without the de-emphasis filter divided by the output noise power with the de-emphasis filter. There's a lot of cancellation that can be done. So gamma is w to the third power tau 1 to the third power divided by 3. Then we have a w tau 1 minus the inverse tangent of w tau 1. For commercial FM, the bandwidth of the message signal is 15 kilohertz, so the W, the bandwidth in radians, is 2 pi times 2 pi times 15,000. And for commercial radio, the time constant 1 is 75 microseconds. And you put those numbers in, and it turns out that the improvement in the noise power is a ratio of 20.88, which turned into decibels is 13.19 decibels, which is a significant increase in the noise performance, so much so that this pre-emphasis and de-emphasis is built into all commercial FM broadcast and receiving equipment.